Welcome. In this chapter, we are studying uh, several instruments, measuring instruments using op-amp based amplifiers. Okay, and so we are taking examples and small numeric problems to understand this. What I see here, last time we took an example where we wanted to measure some voltage using an ammeter, okay, and this is how we made the circuit. So the voltage input comes here. This is primarily a non-inverting amplifier. The structure resembles the non-inverting amplifier circuit, and the ammeter we put here. So one thing which I didn't tell you or I didn't highlight the last time is that this circuit is acts like a voltage to current converter. Okay, so you can say that this is a voltage to current converter. Or you can say this is voltage dependent current source or something like that. I mean, this, the idea is that the main thing is that you give a voltage and you get a current. The value of the current is proportional to the voltage. So if you give V in, you get some current which is proportional to this. Why? Because you know, if this is V in, then due to virtual sorting principle, same voltage V in should appear here, and therefore we have V in here. This is 0, so V in divided by R1 is this current, okay, which is same as this current. So therefore this current is same as this voltage divided by R1. So let's see another similar circuit which also will act as a voltage dependent current, I mean voltage to current converter. In this case, we have used primarily the structure of a non-inverting amplifier. We could also use the structure of an inverting amplifier like this. So let me first draw the inverting amplifier. We have negative feedback. This is input Vi, call it R1, R2. This is grounded 0, okay, 0 volt. Due to virtual sorting, this will also be at 0 volt, and this is inverting amplifier. Now what we can do, say if we replace this with an ammeter, then the current that we will have in this part, okay, this current I is determined solely or only by this voltage. How? Because you know this current and this current must be same current goes like this, nothing can go into the op amp, therefore these two currents are same. And how much is this current? From this branch I can say that I is Vi minus 0 divided by R1. So therefore this current will be determined only by this input voltage, okay. So this is again a voltage to current converter. And you see no matter whatever is the impedance of this ammeter, resistance of this ammeter R2, that doesn't matter at all. So I can take any value of R2, different values of R2 within of course some range, otherwise the op amp may get into saturation region. So within a range of values of R2 or the ammeter or whatever impedance is connected here, that will not affect this current. The current is only determined by this voltage and this resistance. Okay. So this is another similar circuit which we can use. Now next thing that we will study is say some programmable gain amplifiers. What is a programmable gain amplifier? It is basically an amplifier whose gain can be altered, changed. Okay. So we will have switches with which we can change the gain at desired value. Okay. So let us first take say a non-inverting amplifier. Which looks like this. A fraction of the output goes to the input. This is the input voltage Vi, this is the voltage output Vo, and here the gain is how much? We know this is 1 plus R2 by R1. Okay. So this is the gain, which is same as Vo by Vi. Okay. Now we want to make it programmable, changeable, alterable. So what we can do, we can take either of these two resistances as variable. Simple. So you change any resistance, this one or this one, you can change the gain because the gain is given by this. So this is not a very big deal, but let's see. So what we can do, so if we for example take, let me first write this as R2 multiplied by C1, okay, where C1 is 1 over R1. That means C1 is the conductance of this. Okay, C1 is the conductance which is same as 1 over R1. Now therefore you see we can take let's take C1 variable. Okay. So what we will do here, instead of having a fixed resistance, we can connect it say to this set of resistances, and so you can connect any of them, right? If you connect this one, you have one value of R1, you can connect this one, another value of R1, therefore the gain will change. In fact, you can connect this in different combinations. You can connect only one or two at a time, three at a time, all four. They will all give different value of this equivalent resistance, right? And therefore the gain will be different. This will be changeable, programmable. Okay, so this will become programmable. Now I want to just choose the values of these resistances in a bit interesting way, nothing difficult. So what I will do, I will say choose these conductances in ratios like 1:2, 2:3, 1:2, 4:8 in this ratio. One is the double of the other and so on. And what I will do, so this is the ratio of conductance. Okay, conductance should be like this. So that means the resistance should be like this. Okay, and let me take it this way. R1, this is R1 by 2, this is R1 by 4, and this is R1 by 8. Okay, and call these switches as okay, you can call them D0, D1, D2, D3, okay, etc. And let me also choose R2 equal to R1. Okay, so choose R2 equals R1, and now let's see what happens if we connect these different switches. Okay, so the conductance of this part, okay, the equivalent conductance between this and this point is can be written as C or conductance between call this point G for ground, and call this point as A. Between G and A, this we can write is equal to, for this is 1 over R1. Okay, for plus conductances in parallel they get added, right? So plus this plus 1 over this, which will be 2 by R1. Now I will write this multiplied by D0, where D0 tells me whether this resistance is at all connected or not. If D0 is 1, that means this resistance is connected. If D0 is 0, that means this resistance is not connected. So therefore this will become 0 and will automatically go away from the calculation. Here also I will write D1 plus this will be 4 by R1 multiplied by whether this is connected or not, plus this is 8 by R1 multiplied by D3. Okay. Now therefore the gain becomes, from this we can write 1 plus, now R2 is nothing but R1, and this conductance C1, okay, this conductance we can write from this as D0 by R1 plus 2D1 by R1 plus this term, all these terms up to 8D3 by R1. Okay, so this then you can write 1 plus this R1 will get cancelled, so you will have D0 plus 2D1 plus, there was another term which I couldn't write due to space, which was 4D2 plus 8D3. Okay, so you see this is like 1 plus, this is like a binary number represented by D0, D1, D2, D3 plus the binary number represented by D0, D1, D2 and D3. Okay, so then this becomes a programmable gain amplifier, and also the gain can be changed in accordance to the binary numbers. Okay, so you can make, for example, if all D0, D1, D2, D3 all of them are off, Okay, so if d0 equal to d1 equal to d2 equal to d3, all of them are 0, which means off or open, okay, then the gain is, these all will be 0, then the gain will be just 1, which also means actually all these resistances are not present, they are all removed, so we only have a direct feedback, so this will just act like a buffer. Okay, so this will become a buffer. Similarly, you can take say only d0 equal to 1 and everything else d1 equal to d2 equal to d3 equal to 0, then the gain will be how much? 2. Okay, so you close only one switch and you have a gain of 2. And similarly, if you want, if you say connect this to d0 and d1, then the gain will be how much? So this will be 1, this will be 1, so 1 plus 1 is 3, plus this total will be 4. If you close this switch and this switch, then the gain will be 4. So this way you can change the gain. So, okay, now so this was one programmable gain amplifier which we which we have made using a non-inverting amplifier. Similarly, one can also take first a inverting amplifier and then one can make it programmable. So let's draw it. So I strongly request you, stop the video, do it yourself and then check your answer, your solution with mine. Okay. So once you know what we are going to do, always in these videos I request you, once you know what we are going to do not watch that, try it yourself first, and if you can do it yourself, you don't have to watch the videos at all. Okay, so R2, R1, this is this is inverting amplifier and we want to make it programmable. So we can take either this variable or this variable, both will give me some programmable amplifiers. So I have many choices, so let me choose to make this variable and keep this constant. That is my choice. Okay, there is nothing sacred about it. So let's make R1 variable, and once again we will make R1 variable so that the gain can be changed in a binary fashion like this. Okay, so what we will do, we will take many such R1s, okay, let me just take three of them, and then let me connect switches. So you give the input here, this is V in, and you have the switches, and we have to choose these resistances in a way that the gain, the pattern of the gain follows some binary pattern. Okay, so let's try that. Let me first give let me first write the formula for the gain. Gain in this case, you know, is R2 by R1, which I will first write R2C1. C1 is nothing but 1 over R1, that is the conductance of this part. So if I I mean, I just take it in the numerator so that I can take direct sum of these conductances. Okay, because things in parallel, they get their conductances added, but not resistances. So therefore, I write it in this way, a small trick. Okay, now then what I will do? Okay, let me just call this resistances as A, B, and C, or RA, RB, RC. Okay, so then I can write gain is equal to R2 multiplied by the total conductance of this. Okay, they are in parallel. Now for this it will be 1 over RA, provided this switch is connected. If this switch is the first switch should be connected, call it DA, DB, and DC. Okay, so provided DA is connected, this will be like this, plus if DB is connected, we will have more conductance, and if DC is connected, we will have more conductance, like this. Okay, now let's choose that R2 equal to some R, and we will choose this in a way that, say, 1 by RA is equal to R, 1 by RB is equal to, sorry, this is 1 over R, this we will choose as 1 by 2 R, 2 by R, and we will choose RC is equal to 4 by R, 1 over R, 2 over R, 4 over R in binary order. So if so, then we can write gain is equal to R2, R2 is just R, then inside the bracket DA multiplied divided by this is 1 over RA is R, so just R, plus DB, and 1 over RB is 2 by R. Okay, plus this will become 4 DC by R. This R will cancel, so therefore we will have this is equal to DA plus 2 DB plus 4 DC. Let us just now rename this. Okay, let us call this D0, call this D1, D2, because we see that this is going to act like the LSB of a binary number, because the coefficient to it is just 1, but the coefficient of this is 2, coefficient of this is 4, so that's why I rename them. Okay, rename, new names, and therefore this is simply D0 plus 2 D1 plus 4, or 4 you can write 2 square D2. Okay, so you see this is just a binary number. And once you know how you want to do it, you can always do these calculations or back calculations so that you get what you want. Do not memorize anything, do not memorize or try to remember these things. Okay. So we have seen some programmable gain amplifiers. Let's take a new topic. Let's move to some AC voltage measurement. Okay. So example, so suppose there is a AC voltage, this is AC at this point, call it VI, which we want to measure. This is a small voltage, So therefore we want to amplify it before we will measure. So what we will do, let's take an amplifier, something with an op amp, that is our favorite. Let's take a non-inverting one, for example. So we take a non-inverting amplifier, my negative feedback plus, so this is the amplifier, this is R2, R1, grounded, output, input. So this is the amplifier, and now we have to use a voltmeter at the output. So let this be a voltmeter. So let us now connect this all. So we connect the input to the input of the amplifier, then the output of the amplifier goes to the voltmeter, and it's done, right? So, and if this is AC quantity, right, this is a AC voltage, so the voltage at this point will also be AC, definitely. So this is function of time, this VO function of time, this will be 1 plus R2 by R1 whole multiplied by VIT. Now this is a time varying quantity AC, so therefore we must use a AC voltmeter, must use a AC voltmeter in this circuit, and then this will directly give you the input voltage, okay, after multiplying with this factor, definitely. Now let's make let's take a different example where suppose we have a PMMC voltmeter, okay, then how to use it. PMMC voltmeter, you know, this is a DC meter, so this can measure only DC. If you apply AC across it, I mean if this was for example a PMMC meter, and if you apply AC across it, it will give you 0 reading, or if the frequency is low the pointer will oscillate, that we know. So we cannot connect a PMMC meter in this circuit this way, it will not work. But okay, you may ask why do you want to use PMMC meter? One practical reason could be that PMMC meters have several advantages. Number one, you know, the scale is linear, okay, one small advantage. Another advantage is that PMMC meters are generally more sensitive. We have talked about it, particularly at low values of the input current, you know, because it has a permanent magnet compared to an electrodynamic instrument where the strength of the magnetic field also decreases when the input current is low. So their sensitivity is lower compared to a PMMC meter. So PMMC meter is sometimes good when you are trying to measure a quantity which is of low value. So it may have practical situation where we want to use a PMMC meter. Suppose we want to use a PMMC based voltmeter. What can we do? You know, we can use a rectifier based circuit, diode based circuit to convert the AC into DC and then measure. Okay, so how do we modify this circuit? So let me just modify the previous circuit. Okay. So here I will just connect, say, a diode. Now this need not be a AC voltmeter anymore. I can use a PMMC meter. Okay, so this voltage at this point is AC. This is AC at this point, right? But the current that will flow through the voltmeter, this current is DC, and call this I. Okay, now I, you know, this is DC, and what kind of DC? Half wave rectified DC. Okay, and also now, okay, now let's take some bit of numeric example. Okay, so question: suppose the voltmeter reading in the above circuit is 1 volt, a simple number 1 volt. Then Vi is equal to how much? So then if this reading is 1 volt, then what is the input voltage? Okay, or now this is AC. So if I just ask you this, Vi is how much, by default it means what is the RMS value of this voltage. Okay, because by default when we are talking about the value of an AC quantity, it is normally the RMS value. But let me specify it also for you, that the RMS value of Vi is how much. Okay, and suppose R1 is equal to R2 given, this is given. So this is also given in the question. Now solution. So this reading is 1 volt, and okay, another small thing, let's assume that the voltage drop across this diode is negligible. Okay, so let's assume that the voltage drop across diode is negligible. Okay, I cannot make this assumption often practically, or if in the question it is said that the voltage drop is 0.7 volt or something, in that case I cannot make this assumption. I have to take care of the voltage drop appropriately, but for simplicity now I am assuming that this is negligible, 0 for now. Okay, if so, then I can say that this voltage, this is 1 volt. This is given because voltmeter reading is 1 volt. Now 1 volt, what? 1 volt average. 1 volt average. Okay, why average? Because this is a PMMC meter. This you have to note, because in the circuit it is said that this is a PMMC meter. So even I do not specify it explicitly, it is clear and evident that the voltage which is measured is 1 volt average. Okay, not peak, not RMS, nothing else, it is 1 volt average. And what kind of average? Half wave rectified voltage and the average of that. Okay, so the voltage here, you call this point as A and B. Okay, so we know that VAB, how does it look like? It looks like this, half wave rectified. In one cycle the voltage in one cycle current goes, and in the other cycle current doesn't go. When current doesn't go, the voltage here across it should also be 0. If current is not going, then definitely I can say the voltage across these 2 points at that moment is 0. And in fact, the entire voltage drops across the diode, which is reverse biased at that point. So this is the pattern of VAB between these two, right? Okay, and this voltage, this, let me call it V peak. This is the peak value of this voltage. Now, what can I say about the peak value of this voltage VAB in relation to the input voltage? So, what is the relation between V peak and Vi? So, for that, let me go to the next page. Okay, let me just drop let me draw Vi. This is the input voltage Vi as a function of time. This is time, this is also time. If this is like this, okay, call this point VIP, peak value of the input voltage, right? What is the relation between VIP and VP? You see, in this positive cycle, in the positive cycle, I can write that this voltage, okay, call it VOT, okay, VOT is given by 1, it's written here, and also in the positive cycle the diode is forward biased, therefore this and the voltage drop across diode is negligible. So therefore I can also write the potential at this point here, call it, this point is A, call it VA. Also VA is equal to VOT, which is given as 1 plus R2 by R1 VIT. T, okay, this potential, and this is in positive cycle, and we have given that R1 is equal to R2. Therefore, from this I write, this was VAT. From this I write VAT is same as, this is 1 plus 1 by 1, they are same. So 1 plus 1 is 2 times VIT. Okay, and this is also same as VABT. Okay, because this is at 0, so this is also equal to VABT. So therefore I can write that the peak value of this voltage, okay, let me just call it VABP, peak value of VAB. I can write VABP peak is same as 2 times the peak of VIP, right? So this is what I can write. Okay, this is one thing. And this 2, number 2, is nothing but the gain, which is in this case 2. In general, it can be anything else depending on the R2 and R1. Now, what can I say about uh, the average value across A and B, I can say VAB average, VAB average, this is how much? Look at this. The average value of this half wave rectified signal, we know this is given by the peak, this is equal to V peak, VAB peak divided by pi by 2 and half, because half wave rectified. This formula is true for full wave rectified AC, but this is half wave rectified, so this is the formula for half wave rectified. So then I write this as VAB peak divided by pi. This is the VAB average. This is same as voltmeter reading, which is same as 1 volt given. This is the voltmeter reading, right? So from this I can write VAB peak, VAB peak is same as pi times 1 volt, and VAB peak is same as 2 times VI peak, input voltage peak. So I write this is equal to V input peak, and then I can write this is same as 2 V input RMS multiplied by root 2, because RMS, okay, let me write it this way, RMS multiplied by root 2, because RMS times root 2 is the peak for the input AC voltage. So from this I can write that this is equal to this, so I can write VI RMS is equal to pi into 1 divided by 2 root 2 volt, and you can find how much is this. Okay, so this is how to solve it. Now let me just take, okay, let me just mention an important observation, which is, so in the previous example we have ignored diode voltage drop. So the previous calculation was not perfect, it was somewhat erroneous, and we should take care of it. But I am going to give you a trick, a small change in the circuit, so that the diode voltage drop, even if it is not 0, will not create any problem. Okay. So let's start with the circuit. Okay. Let me modify this circuit such that this diode drop, even if it is not 0, even if it is large and significant, it will not come into the calculation at all. What I will do is this, I will remove the diode from here, let me connect it, and I will put the diode here. Okay, and now what will happen is this. Let's first understand how this circuit is physically different from the previous circuit. Okay, so if you give any voltage here, say some positive voltage at this point at any instant, then this is the positive input, therefore the output of the diode will go up towards the positive value and the output will increase. How long? Until and unless the potential here which is also here becomes equal to this, right? Because whatever is the potential here, a fraction of it comes here. This is a potential divider, so a fraction of the output comes here which goes there, and if you give some positive voltage, this output will keep increasing until and unless this value has reached equal to this input, right? At that point the diode will be happy. That's the principle of a diode. At that point the op amp will be happy. That's the principle of the op amp. Okay, so in this circuit, the diode drop will not affect at all, because the op amp will increase or decrease its output slightly more, okay. How much? I mean as much as the diode drop now I write here, to make this voltage, call it, what can I call this? Is Vn, right? Vn. To make Vn is equal to Vp, which is here, which is same as Vi. Okay, so whatever extra voltage this diode consumes, that will be adjusted by the op amp. What will happen is that the voltage at this point will definitely be this much, but the voltage at this point will be VO plus diode drop, maybe 0.7 volt if this is 0.7 volt. Okay, so this voltage will be slightly more than this voltage, but this voltage will definitely be this multiplied by the gain given by R2 and R1. This has to happen because, I mean, okay, you can do a back calculation. So we start from the fact that the diode will adjust, the op amp will adjust its output to make Vp equal to Vn. Okay, starting from the fact that op amp will adjust itself to make Vp is equal to Vn. So starting from this fact, let us calculate what will be this voltage. So we know this voltage, which is Vn, this will be Vp, because op amp will make so that means Vp is same as Vi. So I have Vi here, so this is Vi. Then how much is this? Potential divider rule. Same current flows in these two resistances. So therefore, if this is Vi, then this current is how much? Vi by R1. So this current I is given as Vi by R1. I am doing complete back calculation. So this current is Vi by R1, and from this I can write Vo is definitely this current I multiplied by total resistance R1 plus R2, which is same as Vi by R1 into R1 plus R2, which is the normal formula. This you can write 1 plus R2 by R1. So you do a back calculation starting from the fact that op amp will anyhow adjust its output so that Vp is equal to Vn. And then you see this diode drop doesn't matter. Whatever extra voltage this diode consumes, op amp will provide that. So this doesn't come into the calculation at all. So this is the beauty of this circuit. Okay, and this has a name. This is called precision. This is called precision rectifier. Precision rectifier based circuit because you know the imprecision or inaccuracy which we had in this previous circuit is not there at all. So this is called precision rectifier. Okay. We'll take a break at this point, and we'll take more and more interesting examples on this topic in our coming class. Thank you.